1905 seminal work, Does the Inertia of a Body Depend Upon Its Energy Content?, Albert Einstein further outlined to the world his theory of relativity, completely overturning the laws of physics at the time and our view of the universe. Among the many statements the great physicist made, he's perhaps most well known for the equation E = mc squared, describing how mass and energy relate. Of course, that equation and how the world viewed it would go on to be shaped by events at the end of World War II, where through atomic bombs we saw how a tiny amount of mass could trigger the release of an incredibly large amount of energy. But for today's video, we're focusing on the flip side of that, and we're instead making mass from energy, albeit a tiny amount of mass from an incredibly large amount of energy. Scientists at the Brookhaven National Laboratory's Relativistic Heavy Ion Collider, otherwise known as the RHIC, have reportedly shown how this could be possible if we look into the light. The prospect of creating matter by smashing light particles or photons together has intrigued scientists for years. It was first theorized in 1934 as the Bright-Wheeler process by the American physicists Gregory Bright and John Wheeler. At the time, it was believed impossible to prove it, however, as an experiment to do so would be extremely difficult to set up and even more difficult to execute. But close to a century later, and it's perhaps no longer quite as impossible as it had one time seemed. In fact, there have now been various setups aiming to show how the Bright-Wheeler process is achievable, although still scientists debate whether we've ever truly seen it in action here on Earth. But more on that later. At the center of almost all Bright-Wheeler-seeking experiments is the use of particle accelerators. These incredible machines have triggered more and more headlines in recent years, and for good reason. Specifically here, they enable the high-energy conditions required to potentially set off the process of turning light into matter. Simply put, a particle accelerator, unsurprisingly, accelerates elementary particles, such as electrons, protons, and photons, at extremely high energies. The powered-up particles travel inside a vacuum, inside a huge pipe, while detectors within the accelerator then record and reveal what happens when the beamed particles either hit a target or collide together. In 1997, researchers at the Stanford Linear Accelerator in America would demonstrate one of the first examples of light seemingly being converted to matter. The team propelled electrons along a straight beamline to create high-energy photons. These photons, after multiple collisions, then created electrons and their positive counterparts, positrons. The photons had, in effect, created matter. The slight controversy surrounding the experiment, though, is one that has followed most others ever since, with questions raised over how the photons used were generated to begin with. Ideally, the Bright-Wheeler process expected the creation of matter from photons alone, no prior electrons necessary. Direct experimental proof of this type, however, has remained elusive as it requires the photons to be extremely energetic, on the level of gamma rays. But we just don't see that kind of energy on Earth, and a gamma-ray laser is one technology that we're currently lacking. So scientists have continued to seek ways around this stumbling block. For example, one design of a particle accelerator that could theoretically smash genuine photons together was proposed by a team at Imperial College London in 2014. It involved shooting charged electrons into a slab of gold to create high-energy, but this time separate, photons, and then smashing those photons into each other to again create subatomic matter. The experiment was reportedly started in 2018, but there are as yet no reports of a successful observation. And now, physicists at Brookhaven National Laboratory believe that they've beaten their contemporaries to the punch, and that they have achieved the first direct evidence of matter created from light. At the center of the Brookhaven experiment are heavy ions of gold, meaning particles of gold that have been stripped of their electrons to create a powerful positive charge. In the experiment, the full details of which were made public in July 2021, the charged ions were accelerated to 99.995% the speed of light inside the relativistic heavy ion collider. An offshoot of this process was that what's been labeled a cloud of photons appeared around the gold ions. And so when the ions passed close enough by one another, those extreme high-energy photons did collide. The collisions themselves weren't actually detectable, but the resulting generation of electrons and positrons, the resulting creation of matter, was. And therefore the claim is that the Bright-Wheeler process has finally been demonstrated. Although, again, not everyone agrees. The problem rests with how the Brookhaven method generated the photons it used. because some scientists believe the photons produced here aren't necessarily real. They're considered by some to be virtual, as when triggered in this way, following the acceleration of heavy ions of gold, they pop in and out of existence only very briefly. The Brookhaven experiment then, according to some, still isn't an example of two standard photons colliding, even if the process has been shown to create matter. Naturally, the Brookhaven team has defended its method, and what's more has shown how the photons they've recorded can justifiably stand in for so-called real photon particles. One reported way to do this is by measuring the angles between the electron-positron pairs between the particles of matter that were created. In short, the angles can be translated to reveal how real or virtual the photons are. And when physicists at Brookhaven painstakingly zoomed in on more than 6,000 of their electron-positron pairs, they found that they were consistent with what we'd expect to see from real photons. Nevertheless, the scientific community has remained cautious about the results. We've taken another significant step towards demonstrating the Bright-Wheeler process for sure, but not everyone is convinced that we've truly proven it. Particle physicist Lucien Harlan Lang of the University of Oxford, for example, has commented that the experiment is, quote, strictly speaking, one step removed from the true Bright-Wheeler process. As such, the debate on the validity of this experiment has skirted toward an arguably even bigger topic than the creation of matter, moving instead toward the definition of reality itself. What's real and what's not, from a scientific perspective or just in general? The results from Brookhaven appear to prove that we can smash photon into photon to create genuine matter. But because the nature of those photons can be called into question, that incredible occurrence is perhaps still not as pure as it could be. Regardless, we're still considerably further along toward capturing the Bright-Wheeler process once and for all, and the experiment has added to our growing knowledge, because ultimately, the quest to show beyond doubt this phenomenon in action, this emergence of matter from light, is also a bid to recreate what was happening in the first moments at the birth of our universe. We of course know that matter did arrive and that something did come from seemingly nothing, and there are plenty of reasons and theories as to why and how that unfolded. But it's thought that the Bright-Wheeler process accounts for at least part of the story, birthing some of the earliest electrons and positrons into the cosmos. Moving forward, the coming years are set to be crucial as we further flesh out our understanding of the subatomic world that guides everything and the most fundamental laws of physics. But perhaps the most significant change for this field in particular won't happen until we develop gamma-ray lasers. These would truly represent tech of the future, but only then will we be producing light that's as genuinely real as the light allowing you to view this video, while also harboring the extreme energy required to trigger the Bright-Wheeler process at all. And so the work continues. But that's how scientists, on some level, have proven that light can create